Computers are made of billions of transistors that act like small light switches, either turned on or off, and are represented by the binary digits of zeros and ones. These binary digits form the fundamental language of computers, enabling them to perform calculations and browsing the web. Logic gates, the building blocks of computer circuits. They receive inputs and produce outputs based on specific logical rules. I will now briefly go over them. NOT gate. This is the simplest logic gate, accepting a single input, either 0 or 1. It inverts the input, meaning if the input is 1, the output is 0, and if the input is 0, the output is 1. A truth table is used to visually represent this rule. AND gate. This gate takes two inputs, typically labeled A and B. It outputs a 1 only when both A and B are 1. In all other scenarios, it outputs a 0. Here is a larger truth table that illustrates all four possible combinations of two inputs and their resulting output.
Similar to the AND gate, the OR gate also takes two inputs. It outputs a 1 if either A is 1, or B is 1, or both A and B are 1. The output is 0 only when both inputs are 0. Here is a truth table of the OR gate. NAND gate. This gate is essentially an AND gate followed by a NOT gate. It produces the opposite output of an AND gate. It outputs 0 only when both inputs are 1, otherwise, it outputs 1. Here is a truth table visualizing the logic gate. NOR gate. Similar to the NAND gate, the NOR gate is an OR gate followed by a NOT gate. It outputs a 1 only when both inputs are 0, in all other cases, it outputs 0. Exclusive OR gate, also known as XOR gate, outputs a 1 when exactly one of its inputs is 1, if both inputs are the same the output is 0. This is presented as a solution for calculating if exactly one of two inputs is 1. Exclusive NOR or XNOR gate. This gate is the inverse of the XOR gate. It outputs a 1 when the two inputs are the same, both 0 or both 1, and 0 when they are different. Here is a truth table further explaining XNOR gate.